we've got a really good group of people at the university who are focused on it, and I think they'll get there. So this is, what I'll say is this is academic work, this is not what Ambiq is about. However, it's the really driving force behind everything we do. Long term, I expect our chips to be sitting inside products just like this. And we're having some, I'll say we're having some discussions with customers, not exactly this device, but medical devices that are very size constrained and pretty small and pretty interesting. So there's some real opportunities there.
So what's the cost of this potential chip like this? You mentioned like
what's the cost, did you say?
you said like a $6 to $8 watching.
Well, that's a different market. Here, well, we're not in this particular market is not a price sensitive market. I can charge a lot of money for these things. What I can tell you in terms of raw materials, and we know how much the die here is about 1 millimeter on a side. We know how much a die that's 1 millimeter on a side costs. You've got a battery that's 1 millimeter on a side. It's a battery die, so it's going to be similar cost. I don't know about price now. I won't know anything about price, but in terms of cost, it's going to be similar. The other stuff is men's fabric. There's some men's fabrication that's happening there. That's going to be a little bit more expensive. At the end of the day, the prices, the cost of goods is not going to be the important thing in an application like this. It's going to be all about price. This is a pretty compelling thing. I think technologically we're essentially there. There's just the question of this particular device is when is there going to be the real draw from companies out there, from customers to actually manufacture. We are seeing some devices emerge that ST Microelectronics, for example, has a contact lens-based device that they're helping out with. It doesn't have a battery; it's a completely passive thing. And from a research perspective, it's fun to butt heads with them. But that's an actual product that's going to be out there pretty soon. In fact, it may even be on sale today.
Don't you have an FDA issue?
Yeah, there's a big FDA issue, and that's why Ambiq is not going down that road. We to be honest, set out to be a medical chip provider. That's absolutely where they need us, but I don't have patient enough investors that are willing to wait 5 years for FDA approval. So that leads logically to taking the next step. I was a PhD student that graduated in end of 2008, beginning of 2009, and spent some time as a postdoc continuing to refine the technology. We had good technology, had a lot of interest from a lot of companies. The challenge was finding the right first customer. So we spent most of 2009 doing that. In 2010, founded the company. Raised a $2.4 million round in November of last year and moved down here. So I would have loved to keep it in Michigan, but we just don't have the incredible pool of talent that you guys have here in Austin. So it was an easy decision to come here. And I think that we talked to a lot of people. Should it be Silicon Valley or Austin? We had 10 people say to us, you really got to be in Austin, you're going to love it. We had 0 people say the same thing about Silicon Valley. So, so we ended up here. Our investors include actually a pretty long list of investors. The 2 biggest investors are D&J Mercury, which is a Houston-based venture firm, and then ARM is also a co-investor. So they're an important part of what we do. We are going to be building a Cortex M0-based ultra-low power microprocessor line. We just, as I mentioned, moved down here and have begun operations. We've got an office. This is our office. You can tell it's in Texas by the star right there. It's over by Westlake High School. If you know where that is, it's right next door. So we're in town. We're building ARM-based low-power silicon, and we're hiring. So I didn't want to take too much of the presentation and talk about this, but I'm happy to discuss. If anybody has questions about the company's product line specifically or about jobs or hiring, please do come see me. But that's really what I wanted to cover today. We took this a long way through research, did a lot of low voltage research, did this deep sleep mode research, ultimately formed the company, and the next step for us is to build the most energy efficient standard and custom microcontrollers for a wide variety of wireless electronics. We're getting to the point where this ubiquitous computing thing can happen, and this whole energy efficiency thing is really the final piece of the puzzle. So, thanks for your attention. Happy to answer any of those questions.
Can you tell us a little bit about the timer and how its power consumption compares with, for instance, like a watch timer?
Yeah, so we have a number of timers internally. We have a crystal-based timer that you find in a watch, a 33 kilohertz based oscillator. That's I'm not going to say that that's a confidential number. I'm not going to give you the number, but suffice it to say it's a lot lower than you'll find out there today, using many of the techniques that we've learned over the years. We do have also an entirely integrated on-chip RC oscillator, and that I'll give you the number is, I'll give you a relative number. It's about 100 times lower than the RC oscillators that you find out there today. It's also temperature compensated. So we've got a number of key technologies that allow us to get pretty low there, a number of key building blocks. I'm being purposely evasive on this, but I'm happy to share papers with you that disclose publicly available information. It turns out the timer is actually really important, though. We run into, when you go to, you look at companies like, there are no microchip people here, right? So I'll pick on them. They advertise sleep mode of 20 nanoamps, which is really good, right? It's incredible. But when you dig deeper, you realize that it's a mode where nothing's functional. You're essentially in a glorified reset mode. Memory's cleared, there's no timer. Reset is asserted. There's no way to escape this sleep mode, right? It means that there's some other circuit in your system that's going to wake it up. And so it doesn't matter if the thing is 20 nanoamps, if you're absolutely consuming 5 microamps over here. So what's really important is what we call functional sleep modes, where you've got an oscillator running in the back, you've got memory retained, maybe you've got some peripherals running, maybe it's a charge pump that's recharging your battery, or you've got a touch controller that's monitoring a button that you press or something like that. And all of these things need to consume minimum power. So that's where we're really good. The sleep timer is the first of those. We do have a number of other circuits that we do with similar real power. And I think that's the real key, is to be able to deliver functional sleep modes.
Just the relative power difference between the RC timer and the crystal timer?
Yeah, right now it's about, the oscillators themselves, it's about 30x different. When you look at the entire system power, it's going to be a much smaller difference because there's just other stuff that consumes power and doesn't change the RC. So you can sort of figure out, what crystals are doing, probably back up to that. It's a very important. I don't want to give maximum because any of you guys have a lot of action in that space. But yeah.
So you showed that this system is going to have some sort of communication or sensing. How much power is going to be in those
Is the
blocks?
sensing?
Right, sensing, and also you showed somewhere, I saw the UWB, communication module.
Yeah.
But
Yeah.
is the processor going to be the bottleneck for those applications?
Yes,
or those two?
that's the right question to ask, and that's definitely one of the things we run into, for example, in customer conversations. It depends on your application. Anything that's going to be sleeping for a very long time, the microcontroller sleep power does become appreciable. It's anywhere from 99% in some cases to 50% in others, and then in those cases where you're waking up frequently, it's almost nothing, and all of your power is buried in the radio. Good example. Well, in anything real-time based, if you're in a car and you need to be reporting constantly what the I don't know what the tire pressure isn't a good example because it's going to be less frequent, but if you've got some sort of sensor on the camshaft or something like that, or you've got some temperature sensor in the cylinders, those things need to be reported pretty frequently. And so your sensor that's measuring that is consuming most of the power, as well as the radio that's transmitting at several times a second. The critical crossover point we find, just roughly, is if you're doing communication less than once every 5 minutes, the microcontroller is actually an appreciable portion. And you think about that, and there's actually a lot of applications where you're doing communication less than once every 5 minutes. In fact, one of the things that you can do, because you've got a microcontroller that's so power efficient, we can do some local computation and avoid a lot of that object communication. Sensors is a whole other issue. It depends on what kind of sensors you're using. A lot of the sensors we can do on chip. A lot of the sensors, MEMS sensors, are zero power, and it's a matter of how much power you're consuming in the interface. In a capacitive interface, for example, so I mentioned capacitive digital converters earlier. If you've got a pressure sensor, for example, in the case of the intraocular sensor, the pressure sensor itself, the transducer, consumes no power. It's the capacitive to digital converter, and we can actually do that using a lot of our techniques. We can do that really efficiently. there's no reason to think we can't hit sub 1 nanoamp for average power during pressure measurement. Now, it's not going to be, I'm not going to be doing it, I'm not going to be interpreting complex gestures and doing megahertz type throughputs or megabit type throughputs, but we can certainly get the power down pretty low. So good question, it's the right question to ask.
So do you think it's possible some techniques can also apply, you expand it into chips like using that, this kind of
Yeah, it's a good question. That's the first thing that a lot of people ask us is, look, if you can do such low power, why not just go after the big cell phones and iPads and all this stuff? And you know, one comment there is that in those systems, pretty often the microprocessor is a small piece of power pie. For example, you've got a display that's just draining power. You've got a huge radio that's communicate to a tower somewhere else, and that's draining power. It's received. You know, this is a horribly power inefficient device in a lot of the other components, and there's not much. It's Amdahl's law. There's not much we can do there. Additionally, as I mentioned, a lot of what we do is low voltage, so I can't hit the gigahertz frequencies you might need in some of these things. Long term, I think we will. There's a lot of ongoing research. There's some really exciting research in the low voltage space coming out of Michigan, where they're taking a huge array of ARM cores and building 3D stacks of highly parallel ARM cores. And so you've got essentially a server in a tiny little package. And that's pretty exciting stuff. It's all low voltage, but that's going to be coming down the road in the next few years. We're not quite there yet.
So you mentioned long-term battery life. So you're going to obviously have to count on your design to be highly reliable, not just in terms of power consumption, but also with the function and able to do any sort of HTOL, or I'm not sure if that's appropriate for competitive applications, but for any sort of reliability studies to see if there's any effect on the power consumption.
Yeah. So in academia, we tend to ignore that sort of thing. It's about getting one chip to work, right?
Right.
But more seriously, there are certainly reliability things to worry about. A lot of the traditional reliability issues that we worry about, high performance circuits, high voltage circuits, are just not a concern. I don't need to worry about the long-term wear out of my circuit. The voltages are very low. We're not using really thin oxides that are subject to breakdown. We're using really old technologies. So in that sense, we're helped out. Power is not going to change much over the course of time. I mean, you don't have these, like I said, you don't have these wear out devices that are going to change the characteristics of the devices. When we talk reliability, the most important thing probably is temperature, because we're exponentially sensitive. When you get down to those really low currents and low powers, you're exponentially sensitive to temperature, and so it becomes important to have good compensation circuitry. And that's definitely one of the things that we do really well is compensation for temperature. Soft errors is if we're going to get really crazy. Soft errors is another issue that pops up at low voltage. You've got less charge on the node, so you found alpha particle could disrupt things. You know, the reality is that we're using slightly larger memory cells, and so you counter that lower voltage with larger capacitance, and so the amount of charge is actually not that much different. So we haven't done extended studies there, but there's definitely evidence to indicate that that's not going to be a huge problem. No more of a problem than it is for high voltage. And if it is a problem, it's a linear problem. It's not an exponential problem.
So you also think because you're using older, more mature technology, you're going to have less concerns with variability in your process, so that you're not going to have to worry about some.
Well, that's the big challenge. I mean, I think going lower in voltage is very similar to accelerating your process node. So 0.5 volts at 0.18 micron is a lot like, I don't know, 1 volt at 65 nanometers, you know, in terms of variability, sensitivities, and so forth. So it is a problem, and that's one of the things that we're really good at addressing those issues. So there's a reason that TI and Silicon Labs and some of these other companies today are operating at 3 volts. It's tough. And so it requires a pretty big paradigm shift when we design chips. Do a lot of that. Happy to talk about a lot of that. Also, happy to talk. Yeah.
How have you found the models to be at predicting heat subthreshold behavior over temperature and that sort of thing? Do you have to do your own, have you done your own model extraction?
We haven't done really extensive model hardware correlation. What I'll tell you is that it's pretty